Our last topic this week is right-angle trigonometry. So the idea here is the following. We are going to give equivalent definitions to the sine and cosine functions that are independent of the unit circle and are related to angles in a right triangle. Suppose first that we do have a unit circle, and we choose a point with coordinates xy on the unit circle that corresponds to angle t, as always. So here, of course, x is cosine t and y is sine t. And now let's do the following thing. Let's first note that cosine of t being x is also x divided by 1. That's not very deep, but when you write it as x divided by 1, you see that in this right triangle, x divided by 1 is the ratio of the adjacent leg this leg is adjacent to angle t over hypotenuse 1, much like y divided by 1 is the ratio of the leg of this triangle which is opposite to angle t. Right? X is adjacent, y is opposite to the hypotenuse. So we're going to explain in a minute that actually in any right triangle, these ratios of adjacent leg by hypotenuse and opposite leg by hypotenuse are respectively cosine and sine of the angle in question. Say, for example, we have a right triangle which is similar to this one, red triangle. Let me use the green color for that other triangle. And say this point is O, this point is A, and this point is B. Now, by construction, the red triangle is similar to the green triangle. And we can therefore write ratios of corresponding sides. For example, cosine t, which in the red triangle is x, is of course x divided by 1. And we view this ratio as x divided by 1 as the ratio of two sides in the red triangle. The adjacent side, the adjacent leg over hypotenuse. Right? So I can write this ratio equals the ratio of BO, the leg adjacent to angle T in the green triangle, over the hypotenuse, AO. Adjacent leg over hypotenuse. And the same thing goes for sine. Sine is on the one hand y, and if I write it trivially as y over 1, I understand that y over 1 is this side divided by this side. In the green triangle, it's the side AB divided by the hypotenuse AO. Which in the green triangle, with respect to the angle T, is the opposite leg, AB, divided by the hypotenuse. All right. Now, suppose we're given some triangle, some right triangle with angle T. We understand that this leg is adjacent and this leg is opposite. We can always do the same procedure in the reversed order. We can always put a unit circle here and introduce coordinate axes so that this here is the x-axis, this here is the y-axis, and this here is the unit circle. So that the coordinates of this point are cosine t, sine t, and I again have two similar triangles. The blue one and the red one. And if I denote the sides as the vertices as O, A, B, C, and D, I see that, for instance, OD divided by OC by similarity of triangles blue and red is simply OB over OA. But OA is 1 because it's a unit circle, and OA is a radii. And OB is, of course, the x-coordinate of point A. Which simply is cosine t. So what we get here is that in any right triangle, remember we started with the right triangle OCD with no connection, no relation to any unit circle, any coordinate system. What we obtained, the fact that the ratio OD over OC, which simply is the ratio of the adjacent leg over the hypotenuse, is the cosine of this angle t. Likewise, if we look at the ratio CD over OC, again by similarity of the two triangles, that ratio is the ratio AB, right, CD over OC equals AB over OA. But again, OA is 1 because it's a radii of the unit circle. So we simply get AB, and of course AB is the y coordinate of the point A, and that is by definition sine t. So again, we get the important result that in an arbitrary right triangle, we can now forget about the unit circle, the axis in an arbitrary right triangle. Sine of an angle is the ratio of the opposite leg over the adjacent leg. Is the ratio of the opposite leg by hypotenuse. Sine t is the ratio of the opposite leg by the hypotenuse. That is a very useful definition. It allows us to think of sine and cosine in the context of right triangles without any unit circles. Now, what about tangent and cotangent? Well, tangent is sine over cosine. That is the definition we know. If we now write sine as the ratio of opposite leg over hypotenuse, and cosine as adjacent leg over hypotenuse, upon the cancellation, we get that tangent t is simply the ratio of opposite leg over adjacent leg. This, by the way, gives an important way to interpret tangent on the unit circle, which we didn't talk about when we defined sine and cosine. because we didn't know the relation with right-angled trigonometry. But now we can talk about how we can interpret tangent on the unit circle. So let's draw the unit circle in coordinate axis. I claim that the vertical line through the point 1, 0 will be the axis of tangents. What do I mean by this? Say we have an angle T. So that the coordinates of this point are cosine and sine. This distance is cosine t, and this distance is sine t. Look at this green right triangle, OAB, let's call it. In this green right triangle, if we write the definition of tangent t, tangent t being opposite leg over the adjacent leg, we see immediately that the leg opposite to t is AB, and the leg adjacent to t is OB, but OB is 1, because that's a unit circle. So we simply get AB, and the conclusion is that this distance here is tangent t. I highly recommend that you get used to this idea, that the vertical axis through the vertical line through the point 1, 0 measures tangents. In particular for angles in the first and third quadrant, tangents are positive, and for angles in the second quadrant and in the fourth quadrant, tangents are negative. The signed distance from the point 1, 0. I don't think I want to say it, write it in words. I think we have already explained it. Rather than saying it in words, we can use the picture. Once again, if this is angle T, then the point of intersection of the terminal side of the angle with the vertical line through the point 1, 0 gives you the distance along this vertical line, that is tangent t. The coordinates of point A are, in particular, 1, because it's on the line x equals 1, comma, tangent t. That is very useful. Now, what about cotangent? Well, cotangent, being the reciprocal of tangent, will be the reciprocal of this fraction. So we simply flip it. Opposite over adjacent, flipped becomes adjacent over opposite. And this also has a clear geometric meaning on the unit circle. I claim that the horizontal line through the point 0, 1, the line y equals 1, measures cotangents. Let's see how. Well, because this angle is t, and these two lines are parallel, this angle is also t. Remember, we constantly use this property. If a pair of parallel lines is crossed by a third line, we have pairs of equal angles. If this is t, then this is t. Now, once we know this is t, we consider another right triangle. Let's use another color, maybe purple. OAC. So now in the purple triangle, if we write the definition of cotangent t as adjacent leg over opposite leg, we see that the adjacent leg is, let's call this point D. That is, of course, not point A. That is a different point, D. So the adjacent leg is CD, and the opposite leg is OC. But OC is 1 as a radii of the unit circle, so we simply get CD. And so this distance here CD is cotangent T. So that is a very useful fact. When you work with the unit circle, you now know where tangent and cotangent are, not just sine and cosine. So in particular, D has coordinates point D has coordinates first coordinate is cotangent T, second coordinate is 1. Much like A has coordinates, first coordinate is 1, second coordinate is tangent T. Once we get to inverse trigonometric functions, and we'll be asking questions about tangent of arctangent or arctangent of tangent, this fact that tangent is along this vertical line will be very useful. All right, let's solve an example. We're given a triangle in the picture, and we need to find the value of all 6 trigonometric functions. Apparently all 6 trigonometric functions of t, of course. Well, straight from the picture, we see that, say, cosine t being adjacent leg over hypotenuse is 24 over 25. We should, by the way, check that the triangle is actually a right triangle. So we should check that the triangle satisfies the Pythagorean theorem. In other words, that 24 squared plus 7 squared is 25 squared. That's important. So 24 times 24 is what? 576, and 25 squared, I believe, is 625. So 576 plus 7 squared, which is 49, is 625. So the triangle is indeed a right triangle. Because Pythagorean theorem works both ways. If your triangle is a right triangle, then the square of the hypotenuse is the sum of the squares of the legs, and vice versa. If in a triangle the square of the longest side equals the sum of the squares of the 2 other sides, then your triangle is a right triangle. So we computed cosine t, that's 24 over 25, and likewise sine t is opposite leg over the hypotenuse. In this triangle, the leg opposite to t is 7, hypotenuse is 25, so sine is 7 over 25. This immediately allows us to find secant and cosecant, secant being the reciprocal of cosine is 25 over 24. And sine gives us the value of cosecant because cosecant is reciprocal of sine, so cosecant is 25 over 7. Likewise, we can now easily find tangent and cotangent, either as ratio of, say, sine over cosine, or straight from the triangle. Tangent is the ratio of opposite leg over the adjacent leg. And so that is 7 over 24. And cotangent, on the one hand, is cosine over sine, or otherwise adjacent leg divided by the opposite leg. So that is 24 over 7. All right. Right-angle trigonometry allows us to talk about a very important class of identities called co-function identities. What is that about? Well, consider a right triangle. Let's call it ABC. And say the acute angles are alpha and beta. Well, because in any triangle the three angles must add up to pi, we have that alpha plus beta plus the measure of the other angle, which is 90 degrees, or pi over 2 is pi. From here, of course, if we move pi over 2 to the other side with a minus, alpha plus beta equals pi minus pi over 2, which is pi over 2. So the angles alpha plus beta, the acute angles in a right triangle, add up, of course, to pi over 2. On the other hand, let's say work with angle alpha for a second. If I want to write the value for sine alpha, sine being the ratio of the opposite leg over the hypotenuse, and my triangle is opposite to alpha is the leg BC, hypotenuse is AB, so I get the ratio BC over AB. And likewise, cosine alpha is the adjacent leg over the hypotenuse. The leg adjacent to alpha is AC, hypotenuse is AB. But if I now look at these two ratios from the point of view of beta, for beta, if you are now looking at this situation from this perspective, what is BC over AB? BC over AB is adjacent leg over the hypotenuse. That's by definition cosine. So that same ratio is actually cosine beta. And the same with the other ratio. What is AC over AB from the point of view of beta? AC is the opposite leg. AB is the hypotenuse. So for beta, AC over AB is the opposite leg over the hypotenuse, which is by definition sine beta. Now, on the other hand, from the first line, we see that beta is pi over 2 minus alpha because the two angles add up to pi over 2. And from sine alpha being cosine beta, we have an important identity. We have sine alpha equals cosine beta, where instead of beta, I want to write pi over 2 minus alpha, because beta is pi over 2 minus alpha. That is a very important identity called co-function identity. And the same with the other line. Cosine alpha is sine beta, where instead of beta, I write pi over 2 minus alpha. Both are true, by the way, for any alpha, not necessarily in some acute angle in a right triangle. The two identities actually are true for any real alpha. Well, as an example of application of these two identities, suppose, for instance, we have the angle pi over 12. We can immediately see that sine of pi over 12, whatever it is, equals cosine of pi over 2 minus pi over 12, and that is 5 pi over 12. So without doing any algebra, we know straight away that sine of pi over 12 and cosine of 5 pi over 12 are the same number, simply because they add up to pi over 2. This here is, of course, a typo. This needs to be 5 pi over 12. So these two identities we just obtained, they give rise to the other four co-function identities. Why, for instance, we have this identity for tangent, that tangent t equals cotangent of pi over 2 minus t. Well, if you write cotangent of pi over 2 minus t, and use the definition of cotangent as the ratio of cosine and sine, that's simply the definition of cotangent. And now we apply the co-function identities to both cosine and sine, we have that cosine of pi over 2 minus t is sine t, and sine of pi over 2 minus t is cosine t. That is co-function identities for sine and cosine. And of course, sine over cosine is tangent. That is the very definition of tangent. So cotangent of pi over 2 minus t equals tangent t. The other trigonometric identity here, cotangent t equals tangent of pi over 2 minus t, is proved exactly the same way. And the same is true for these two. For example, y is cosecant equals secant of pi over 2 minus argument. Well, if we start with secant of pi over 2 minus t, and recall that secant is 1 over cosine, that is the definition of secant. Now we apply the co-function identity for cosine. Cosine of pi over 2 minus t is simply sine t. Co-function identity for cosine. And of course, 1 over sine t is simply cosecant t. That is the definition of cosecant. All right, co-function identities are very important. So let's solve a couple more examples. This one should be very quick. Secant of pi over 6 is 2. Cosecant of pi over 6 is 2. Find secant of pi over 3. We note, of course, immediately that pi over 6 and pi over 3 add up to pi over 2. Right, because the sum is 3 pi over 6, which is, of course, pi over 2. So secant of pi over 3 as secant of pi over 2 minus pi over 6. So what happened? We have replaced pi over 3 by pi over 2 minus pi over 6. And by the co-function identity, secant of pi over 2 minus argument is cosecant of argument. And we know that's 2. In this next example, we need to find the unknown sides of the triangle shown in the figure. So we are given that the triangle is a right triangle. One of the acute angles is 30 degrees. The opposite leg to that angle is 7. So we need to find the sides AC. Well, we can work with any trigonometric function. Let's say sine. We can write that sine of 30 degrees, which on the one hand is 1/2. On the other hand, from the right triangle is opposite leg over the hypotenuse. Opposite leg is 7. Hypotenuse is unknown. So from here, from the fact that the ratio of 7 and hypotenuse equals 1/2, we find that hypotenuse equals 7 divided by 1/2, which is 14. So hypotenuse is 14. And now to find A, we could use the Pythagorean theorem, or we could use another trigonometric function, for instance, cosine of 30 degrees, which is on the one hand root 3 over 2, on the other hand adjacent leg over hypotenuse. Adjacent leg is A, hypotenuse is 14. So from here, A is 14 times root 3 over 2. Or simply 7 roots of 3. We can check the Pythagorean theorem, verify our work. Whether in fact 7 squared plus 7 roots of 3 squared actually is 14 squared. So that's 49 plus 49 times 3. That's 49 times 1 plus 3. That's 49 times 4. And that is 160 plus 9 times 4, 36. The sum is 196. And 196 is indeed 14 squared. So Pythagorean theorem checks. This angle is, of course, 60 degrees. And you can see, for example, from here that cosine of 60 degrees is 1/2 as the ratio of 7 and 14. And sine of 60 degrees is the ratio of 7 over root 3. Over 14, which is root 3 over 2 as expected. Now, in the next problem, we are given that a right triangle has one angle of pi over 3, which, by the way, immediately implies that the other angle is pi over 6. Because remember, the two acute angles in a right triangle must add up to pi over 2. We know hypotenuse is 20. Find the unknown sides of the triangle and angles. Well, the angle we have already found, it's pi over 6. And in any right triangle, whose one acute angle is pi over 6, the leg opposite to it is simply half the hypotenuse. Why is that? Well, if you write the definition of sine for pi over 6, on the one hand we know it's 1 over 2, on the other hand it's opposite leg over hypotenuse. So from here, opposite leg is simply hypotenuse over 2. In our situation, hypotenuse is 20, so the opposite leg here will be 10. To find the other leg, we can use the Pythagorean theorem, or we can use the definition of sine or cosine for any of these angles. Say cosine of pi over 6 on the one hand is root 3 over 2. On the other hand is adjacent leg over hypotenuse. So the adjacent leg is hypotenuse times root 3 over 2. In our situation, hypotenuse is 20. And so the adjacent leg is 10 roots of 3. And again, we can verify Pythagorean theorem. That in fact 10 squared, the square of one leg, plus 10 root 3 squared, which is 100, plus 100 times 3, which is of course 400, is indeed square of 20, which is the square of the hypotenuse. And in the last problem here, we need to figure out how long a ladder we need if we want to reach a windowsill, which is 50 feet above ground. And the ladder rests against the building, making an angle of 5 pi over 2 with the ground. So, I mean, this here is the ladder, this here is the ground. So, of course, this angle is 5 pi over 2 over 12. So therefore, this angle is pi over 12. And the ladder in this triangle is the hypotenuse. We can use, say, the definition of sine for this angle. So sine of 5 pi over 12 is opposite leg over the hypotenuse. Opposite leg is 50. Hypotenuse is our ladder. So from here it follows that the ladder needs to be 50 times sine 5 pi over 12 long, this many feet long. And as of now, we don't have the machinery to compute sine of 5 pi over 12. Later on, when we get to double angle identities, we will explain how to compute say, sine of pi over 12 and cosine of pi over 12. From sine and cosine of pi over 6. The relation between pi over 6 and pi over 2 is pi over 12 is clear. Pi over 12 is half of pi over 6. So pi over 6 is simply twice the angle pi over 12. And if we did know sine and cosine of pi over 12, then of course the desired angle 5 pi over 12 is also easy to deal with. Say sine of 5 pi over 12 is simply sine of pi over 2 minus pi over 6. And that, as we know, is cosine of, oh, maybe we can do this, no, that is, let me check something. Is this angle really pi over 12? So this angle is pi over 2 minus 5 pi over 12. Yes, I believe I'm correct. Pi over 12. So sine of 5 pi over 12 simply will be sine of pi over 2 over pi over 12, and that is cosine of pi over 12. And how to compute cosine of pi over 12, we will explain later once we get to double angle identities. As of now, you have to rely either on this answer as your final answer or on the calculator. All right, this finishes our study of right angle trigonometry, and this finishes week 9. Next week, we will continue our journey into trigonometry. Thank you.